So today, I'm going to give you a little tour through some futures that are not yet planned, but which could occur. And the purpose is to open our eyes about things that we don't normally hear about, but which are possible and could happen in the coming decades and in this century and in the centuries to come, some of which we think are very exciting. So today, this is not what spaceflight is. It's what we all imagined it should be, and when those of us who've been in the field for a while were very young, this is what we were confident it would be. But it isn't. Not yet, anyway. And part of the purpose today is to talk a little bit about why that is and what might be happening or what could happen that's as exciting and that will lead to these things in any case. The main messages today I want you to remember are these. We actually have choices about what our future in space is. Doesn't always feel like we have choices because decisions are made by governments and large organizations, but we citizens have choices. The investments that governments make determine the technologies that we have access to. That's very important. But the growth rate of what we can achieve in space is not driven by governments, it's driven by capital markets. And that's where capitalism will become very important. And I'll say a few words about that later. And finally, of all the nations on Earth, China is the one, which is investing strategically in some of these futures. And I'll show you why. So first, a little bit of technical background. I'm going to very quickly survey all the places in space that we can reasonably imagine humans living and working in the next couple of hundred years. They're not just these 3 planets that you see here. There are many other places, and I'll tell you quickly about them. But they're not all equal. They're not all useful for the same things, and they don't all pose the same challenges. Where we operate today in space is in low Earth orbit, and in particular the International Space Station and now the new Chinese space station. This is where we're limited today, low Earth orbit. If you go anywhere outside of Earth orbit, you have to worry about space radiation. It comes in 3 types, one of which is close to Earth in the Van Allen belts. The other 2 come from the sun and from the galaxy, and they're pervasive in space. They're detrimental to human health over long periods of time, and they need to be dealt with using a combination of shielding and biophysical measures as well. Anywhere else you go in space, you need to control the effects of space radiation. The farther you go from Earth, the longer it takes a signal, a radio signal or a laser signal, to get there and get back. And that means the farther away you go, the less you're able to control what happens in space from Earth. It needs to be controlled on board by robots, automation, and crews. And that starts to affect the regions between Earth and Moon, which include the Lagrange points. The Lagrange points are fundamentally important places in space. Any 2-body gravitating system has 5 points in space associated with that rotating system that are very special gravitationally. And so, for example, Earth-Moon L5 is the place where Jerry O'Neill suggested we should build space colonies. That's because it's a gravitationally stable place. Even farther out, beyond the moon, we get into deep space, where we have issues with systems lasting for multiple years, keeping human crews alive, being able to be maintained and repaired, and kept functional for multiple years at a time. And this includes a region of space which is truly huge. It encompasses the Sun-Earth Lagrange points, those same 5 points, but in the Sun-Earth system. It includes near-Earth asteroids, which are not near Earth. They're in orbits which are like Earth's orbit. So they can be either very far away or very close to Earth. And then it includes the Sun-Mars Lagrange points, and finally Mars and the asteroid belt themselves. If you get close to a planet planetary body that has a lot of gravity, like the moon or Mars, now you need large propulsion stages to get into a gravity well, get back out of a gravity well. That gets you into lunar orbit or a Mars orbit or the moons of Mars. And then finally, if you want to operate on a place, the places that you're most used to hearing about on the surface of the moon or on Mars, you need additional systems to get down, get back up, and all the stuff you have to operate on the surface. So the point of this chart is to say two things. Not every place that's useful in space is on a planet. And number two, planetary surfaces are in fact the hardest places to get to and operate because they require all of these advanced capabilities. The other locations don't require all of them. Let's talk about the moon a little bit. We call it the eighth continent because it's large. It's very close, actually, just 4 days travel time away. This is a real image of the Earth and the moon in the Earth-Moon system. It takes about 4 days to get there. And the moon is big. It's got as much surface area as Africa. So it's a very large place to explore. And it has resources. So it's a place that can be developed. Think of it as an eighth continent. The seventh continent is Antarctica. And this is now the eighth one, just 4 days away. It's actually no farther to get to in travel time than Antarctica is. But if we're going to develop the moon, we require a lot more than just scientific exploration, which is what has happened so far, and more of which will be happening. We want to get to sustained presence. That means being there permanently, doing things, constructing things, extracting mineral resources, and so forth. We have to go through these other stages to do that. So it starts with scientific exploration, but then we have a lot of learning to do about how to operate in this remote and hostile environment. 1/6 gravity, hard vacuum, temperature extremes, a very dangerous, dusty environment as well. There's a lot we need to learn about how systems function in that environment. We need to know that so that we can scale up to industrial class operations, which we need if we're going to be there permanently. So there's a progression here that starts small and ends big. It may start with vehicles as small as this. This would be a modern version of the Apollo system that took astronauts to the moon in the 60s and 70s. It might be a bigger system. It might be a single-stage system or a three-stage system like this. But it starts with this kind of exploration. Here's the dilemma. The moon is much harder than the International Space Station. By hard, I mean technologically hard and financially hard. So the International Space Station, as miraculous as it is, consumed the resources of the major spacefaring nations of the world for a quarter century to get it developed and built. And what you see there is an amazing machine. But at its root, it's only three things. It's a way of getting up and down, which here I call a shuttle. It's a way of getting power in and heat out. Most of what you see on the space station is that. And then it's a small cluster or complex of habitats and laboratory modules. That's all. That was $120 billion and a quarter of a century. Let's go to the moon. To do even research on the moon in a simple vision like you see here, we require the lunar versions of all the same things we have on space station, plus some way of getting to and from the moon, some way of getting down on the surface and back up, and all the associated surface infrastructure for mobility and construction and the use of lunar resources. So anybody that thinks that developing this on the right is cheaper and faster than what we did on the left isn't paying attention. The fundamental metric of cost in space systems is the number of separate end items to be developed, the number of separate spaceflight systems. It's a bigger list on the right than it is on the left. So that's a challenge. How do we address it? Somebody has to pay. Is it going to be science sponsors who pay? Well, we already know what the budget is of the international space agencies which do scientific research in space. Those budgets are not going to change dramatically. So that's a small amount of money. Then some people say, well, we can make propellant on the moon and sell it to people who use it in space. Okay, that might be spacefaring customers. But who's using propellant? It's the people whose missions are being paid for by the first line, the science sponsors. That's what I call a self-licking ice cream cone. It's not actually an economic engine. The only solution is the one at the bottom. Terrestrial markets, mass markets, traditional economic uses of space, in this case of the moon, for industries like media, travel, materials, and energy. That's not exploration, that's development. So the question is, can we learn to think differently about what space is and what we want to use space for? I would argue that the vision that drove us in the 60s to Apollo cannot work in today's world, because today's world is different. A half a century since Apollo, our world is very different. You see here some things listed. People have access to information instantly. Billions of them have access to information. Within clicks, all of human knowledge. At the same time, we see environmental devastation everywhere around the planet. Climate change, increasingly severe storms, and so forth. And we also see what I've called impactful, societally impactful antisocial behavior. One person can cause dramatic disruption to an entire population or civilization. That's different than it was in the 60s. Finally, we're spoiled by cheap petroleum. We're still pulling it up out of the ground, burning it, and putting it in the atmosphere, which is destroying our climate as we do it. But at the same time, we have access to space and the resources of space. We now know how to do space travel. Our budgets are much lower than they were in the Apollo days in terms of spending power, but at the same time, we have access to immense capital in the private sector. So if you put all that together, what can we do with that? Can we learn to think differently about what space is good for? So this model is why I've called the talk The Four Futures. I believe that out of all of the ideas that have been published and discussed for human spaceflight, all of them arise from one or some combination of these four visions, and they're very different visions. The one on the upper left is what NASA and the other scientific agencies are all about. It's about exploring, learning, going to new places. Even NASA wants to get to the lower right, which is to expand, to have a permanent presence, to normalize spaceflight and have civilization be in space, have people raising families in space, and so forth. But you can't go from the upper left to the lower right directly. Why? Because we've just seen the lower right costs an enormous amount of money, which the space agencies do not have. The only way they can get there is to go through the other two quadrants, which are economic engines. And that's because they tap into the mass markets of terrestrial economy on Earth. On the upper right, we're exploiting for resources or locations in space that are strategically valuable, or energy resources that can only be found in space for the benefit of terrestrial markets. In the lower left, we're developing the travel industry for ordinary people to experience spaceflight. Why would you do that? Because there are many, many more ordinary people who like to travel than there are professional crews doing scientific research for space agencies. So these are ways of turning on the economic engine to be able to invest to get to the lower right. I'm going to show you a couple of examples of things we could be doing in space that hopefully will inspire you. The first is very close to Earth. This would be in medium Earth orbits or the geostationary orbit. This is what I call power from the sky. This is harvesting the unlimited amount of solar energy in space, collecting it, transmitting it to the surface of the Earth, to facilities like this, which are large microwave receiving antenna arrays in agricultural areas, to have unlimited clean electrical energy to run civilization. and in fact to expand civilization, which becomes increasingly important as the developing world aspires to the standard of living that we enjoy in the countries that we live in. If we developed the geostationary orbit for unlimited clean power for Earth, this is how geography would change. What this shows is the geostationary orbit, this outer line, to scale with the size of the Earth, and arrayed around it are all of the major population centers of Earth projected up to that orbit. And what it shows you is who become neighbors in space. So Seoul and Vladivostok are neighbors. You might not think of them as neighbors on Earth, but they are in this future. Chicago and San Salvador are neighbors in this future in which we're providing unlimited clean power to Earth. This allows us to think a little differently about societies on Earth today. Now, the good news is that there is a plan out there to do exactly this, to develop the geostationary orbit for industrial scale, clean, unlimited power for Earth. It's the Chinese Academy of Space Technology's plan. They're already working on it, a little bit behind on the 2020 milestone, but I'm confident that they will, by the mid part of this century, attain the ability to provide unlimited electrical energy to anybody who needs it, who's willing to buy it or accept those terms. And this is the only nation on Earth that's developing it at this time. Here's another one. We talked about Lagrange points, these very special points in a two-body gravitating system. So the L1 point is the one that's between the two bodies. Between the sun and Earth, there's a point called L1, and an object that's placed there will stay there. And it looks at the sunlit hemisphere of Earth continuously. So here what I show is a sunshade placed at L1. It rotates with the system, so it always stays between the sun and the Earth, and it can help reduce the amount of solar input to Earth by a tiny amount, just enough to offset global warming. And it's reversible. If it has unintended consequences, you change it or move it or remove it. So this is reversible geoengineering. How would you do this? Well, one way is to create a ring of dust around an asteroid. And it's possible to move an asteroid around the solar system. So we can move an asteroid to the L1 point, create a dust ring around it that would be stable, and use it as a sunshade to reverse global warming. Because that's a rotating system, at some times of year it'll be edge on to the sun, other times of year it'll be face on to the sun. So you can build it so that it shields the Earth just before the solstice, which is the time when the maximum sunlight hits the North Pole or the South Pole. And you can maximize the effective shading. And then since you need an asteroid to be the gravitating body to hold this ring of dust in place, and we also need a large amount of mass to shield against radiation for a space colony, why not just use a space colony instead of an asteroid, put it at L1, and introduce reversible geoengineering to solve global warming? Here's the third one. This is the experience quadrant. And this is a vision in which hundreds of thousands of ordinary people per year fly into space. What would that do? How would that change people's perception of countries, borders, conflicts, protecting the planet? It's well known that traveling in space changes all astronauts who experience it. If we can bring that experience to larger numbers of people, then that will begin to change the world in a major way. To do this, we need routine flights, something we're working on at Blue Origin. We'll need a new space architecture, something that isn't just for scientific research, but it's also for media, entertainment, manufacturing, marketing, living, adventure travel. This is also something we're working on at Blue Origin. And you would put all this together in what I call a mixed-use space business park. Just like on Earth, we have residential, retail, restaurants, shopping, all of these things combined in large facilities. This can be done in low Earth orbit. This is not magic. This is technology that we already have from the International Space Station. So, I come back to the original theme. We have choices. What I'm going to show you here is a little conceptual roadmap. At the bottom, this is the money that governments spend on human spaceflight. At the top, this is private money that's spent on human spaceflight. And we're going to go through this map. So far, a half a century of progress in human spaceflight is just these two things in the lower left. Spaceflight, how to do it, and space habitation, how to be there. So you can think of the space shuttle and the International Space Station as examples of these two. Now, what NASA and its peer agencies are trying to do is extend these things to the moon, 4 days away, because they want to explore the solar system. I put this one in a dashed line because as you've seen, it's expensive to do this at the moon. Imagining doing it at Mars is far more expensive yet. So let's start where we can perhaps digest this, which is at the moon. All right, in the meantime, now we're beginning to see privately funded passenger travel into space using the technologies that governments developed for spaceflight in the last century. Next, we will see commercial destinations in low Earth orbit, commercially developed, owned, and operated space stations, supporting these broader markets than just research. You put these two things together, and then you can have privately developed, capitalistically developed Earth orbit, destinations in Earth orbit. That's fundamentally different from what we have today, where all we have in space today are government-owned space stations. Well, if we want to industrialize cislunar space, for example, for clean power for Earth, as I showed earlier, we need something else. What is that? We need to develop or demonstrate power from the sky. That's what China is doing right now. Scaling that up will require a public-private partnership, a combination of government money and private money, to learn how to do this at industrial scale, where it's actually useful for the terrestrial economy. And then we will have industrialized cislunar space. We've already industrialized it for telecommunications and Earth observation. We can do the same thing for electrical power for the surface of the Earth. If you have all those ingredients now, which are a robust commercial ecosystem at the top, now you can do anything you want to do. If you want to explore the solar system, you can do that. If you want to settle space, you can do that. Because you'll have reliable, low-cost transportation, you'll have commercial destination systems, and a power-rich operating environment. The way we view things at Blue Origin is what we call the two gates. These gates stand between us and an unlimited future. Without an unlimited future, we have what are called Malthusian limits. We live on a closed system, this planet Earth, with a very thin biosphere, which is very vulnerable to industrial activity, as we are discovering. But to get to an unlimited future, to break out of those Malthusian limits, we have to go through two gates. We need low-cost access to and through space, and we need the use of space resources. Those are the two keys that will give us the unlimited potential of unlocking the solar system's resources to humanity. So, how do we do it? We have to build infrastructure. And this is why we say Blue Origin is a company whose job is to build infrastructure. It's not our job to tell people what they're going to do in space. It's our job to build the infrastructure that lets them discover what they want to do in space. So we need a road to space that's reusable, so we're not throwing away systems all the time. We need commercial destinations at various locations, opening up possibilities for the widest range of users, including scientific research, but also manufacturing and system development, technology development, but also marketing, media, advertising, also adventure travel, tourism, and living in space. That broad range of activities is what a mixed-use business park needs to do so that we can have commercial destinations. And then finally, sustainable growth requires developing resources both from the moon and from near-Earth asteroids. If we put these ingredients in place, we will have unlocked the solar system to humankind. So to do this, we have to build a business ecosystem. This is not about government programs. This is about building a typical business ecosystem in which companies buy services from each other for profit so that people can do things they want to do, just like we experience everywhere here on Earth. Our goal is to normalize space flight so that civilization can then go occupy space.